so they will not be identical. The first question, single transistor biasing. We have a transistor is biased with 3 voltage sources, okay? So it's 3 batteries in this case, right? So you have 1.5 volts, so obviously this voltage here is 1.5. Then you have 2 extra batteries adding 1.5 volts each, all the way to 4.5, right? It's actually indicated here, but clear from the picture that's the case. We have to find the voltage on the collector, the current on the base, the current on the collector, and IE. Basically, kind of an operating point, except that it's not asking for collector to meter voltage. Okay, have 2 cases for betas, and we have to find then the variation of IC in the 2 cases above. Okay, so where do we start? Normally we start with a loop number 1, right, and find that the 1.5 volts from this node all the way to the bottom has to be equal to the sum of the voltage across the 7 kilo ohms plus 0.7, like voltage from base to meter, plus the voltage on the meter. So let's find that equation. We have it loop number 1, right? 1.5 volts equal to 7 IB, voltage on the 7 kilo ohm resistor, okay, plus 0.7 plus 0.8, right? Normally I change all the resistors to kilo ohms and the current in milliamps. Therefore, when you multiply kilo ohms times milliamps, the units cancel each other, right? So we get the result in volts. Okay. So now we know that the current is equal to beta plus 1. Actually, this has to be fixed, right? Beta plus 1 times IB. Okay. Got that. And finally, we get an equation for IB, right? In the previous equation, we are substituting this current by beta IB. So we group to the left side of the equation the constant terms, 1.5 volts and 0.7. So that's in the numerator, right here. And the denominator, we have the coefficients of IB, 7 and 0.08 times beta plus 1, right? Which we have it there. And we do the computations twice, right? One for 90 ohms and one for 180. So we have a couple of results for the different betas, right? This beta is equal to 90 in part 1, and in part 2, beta is 180. Okay? So we have a results for these 2 parts. Okay. Now next thing is we want to calculate the voltage on the collectors and the currents on the collector, currents on the meter, right? So current on the collector, very simple, multiply by beta, right? The current on the base. So we can find the collector for the 90, beta equal to 90, and for the 180, right? This actually, this subindex here is supposed to be 180, right? So we have 180 right there, 2 currents. The next step is to do step number 3. Well, I guess just for completion, like we can find the voltage on the collector, and the voltage on the collector we can find it 2 ways, right? It's 4.5 volts minus the, actually just one way, right? 1.5 volts minus the voltage across the 250 ohm resistor. It's current time resistance, right? So we can do it. So let's do it here. So we found in the previous slide the currents for 2 cases. One is the 180, okay? This is the 180, and the other one is the 90. So we find now the meter currents, beta plus 1 times IB. Finally, we find the voltage on the collector for the beta equal to 90 as 4.5 minus the voltage across the 250 kilo ohm resistor, which I'm drawing this as kilo ohms, right? This is in kilo ohms, but it's the same as 250 ohms times the collector current, 3.2396. We do it with 180, okay? So that gives us 2.82. Same procedure, just change the beta for 180, right? Basically, the current here goes in this one, and the current on the second one goes in the next one, right? So we have that there. Finally, we have the increment in collector currents, okay, in percentage, 32.95%. Okay, so for this, in this, by this we have solved already the parts 1 and 2. So now actually part 1 and 2 are 3, right? Because we find the percentage already. Part 4 is changing the emitter resistance to 50 ohms. So we repeat the previous derivation, right? It's the same equation that we just have here. So it's the collector current is equal to my base current times the current on the base, right? This is the current on the base from the previous slide. Is 1.5 volts minus 0.7 divided by 7 plus beta plus 1 times the emitter resistance, right? This 0.05 is this one here is the emitter resistance. Right? That happens to be 6.637. Now we repeat the same equation for 200. Happens to be 9.38. Okay, and finally we find a variation and happens to be more. Actually, that's important. So we know that if we have smaller emitter resistance, the variation is going to be more. Okay.